So for example, one of these applications that we use every day of numerical solution is a weather forecast, right? And if you're from some place that has nicer weather than Boston, this is something you're going to be using a lot in the near future, especially as we get into the winter. How many people know how weather forecast is done? When you look at your phone and see what's the weather tomorrow, how does the phone know what's the weather tomorrow? Nobody? Wow, usually I get one or two. So actually, you're solving numerical PDEs to forecast the weather. So there are coverage of a weather satellite all over the world and the weather stations all over the world. But they can only read what we call the initial condition, right? They can only read the weather right now. And the weather right now consists of the temperature at not just the ground, but every elevation. So from the ground to 1,000 meters above and 2,000 meters above, the temperature, the humidity, the velocity of the air, the pressure at every single point in the globe. So that serves as an initial condition for the solution of the numerical partial differential equation that governs the evolution of the weather, governs the evolution of the temperature, which you solve equations that conserves energy. Okay, evolution of the density of the air, which you solve by equations that describe conservation of mass. You solve for the velocity, which are partial differential equations that describes the conservation of momentum, right? And conservation of moisture, which is kind of conservation of water molecules. So you have a bunch of partial differential equations to solve, and one criterion is you have to solve it at a speed faster than time evolves itself, right? If you spend 6 hours solving the weather that is going to happen in 6 hours, that doesn't help. So you have to spend, for example, 6 hours solving what actually happens in 6 days. Then it's useful because now you know ahead of time what the weather is in 6 days. And that is what you are reading when you are looking up at the weather forecast. Make sense? And so this is kind of a pretty mundane application of numerical PDEs. And the next slide, I'm going to be showing a most non-mundane application of numerical PDEs. So how many of people know what this is about, what these signals are about? It's one of the most significant scientific discoveries recently, at least from my point of view. It's discovery of gravitational waves, right? So we know light waves. I mean, we have been knowing light is a wave for some time, but gravity can also emit waves. Even Einstein himself was not sure if what he predicted actually existed or not. And it's not until about 2-3 years ago, people actually first detected gravitational waves. But long before people detected gravitational waves, when they built the detector, they built it with knowledge of what gravitational wave would look like, almost exactly. I mean, that's kind of a built-in to the instrument they built to detect the gravitational waves. And how do they know that? They were able to solve the Einstein's field equations and describing what kind of waves would be emitted from, for example, the merger of two black holes or the merger of two neutron stars. Right? These equations are complex nonlinear coupled partial differential equations, and Einstein has no way of actually solving them. And back then, only like very simple stationary solutions, like a very simple black hole, would be amenable to analytical solutions. And dynamic events like the merging of two heavenly bodies is basically impossible to solve. unless you have numerical methods. And it's by kind of repeating these calculations using numerical solution of PDEs again and again with different mass ratios and different kind of type of events, they're able to know basically how these signals would look like far before they are detected. And whenever basically the detection process is they are going to be listening to the signal or to the instruments all the time, and whenever they see a signal that matches one of these in the database, and the database are pre-calculated signals from repeatedly solving these partial differential equations. If they see a match, they report. And that's what happened in the first detection of gravitational waves.